Okay. So when we get to 5.2 and 5.3, we're going to be talking about logarithmic and exponential functions, which are new types of functions. And those two functions will be inverses of each other. So in 5.1, we're going to talk about what an inverse relation or function is. So that's really what 5.1 is all about, is inverse relations and functions. So this first box is the definition. When we go from an output of a function back to its inputs, then we get an inverse relation. So usually when we have like an equation, we put a number in for x, and that's our input, and then we get an output. Well, now if we go backwards and we take the output and then get back the input, that is a inverse relation. And when we do these examples, it'll make more sense. And then when that relation is a function, we have an inverse function. And so if they were to give us a relation that is just a set of ordered pairs, like you see down here, this first example, to find the inverse of that relation, all we're going to do is interchange the first and second coordinates of each ordered pair. And this will produce an inverse relation. So that just means I'm going to switch the coordinates. All my x's are going to become my y's, and all my y's are going to become my x's. So in this example here, H is the set of ordered pairs, -8, 5. So -8 is my x coordinate in that first point, and 5 is my y coordinate in that first point. And I can keep going. All the x's here is 4, -7, and 3.8, and then all the y's are -2, 1, and 6.2. So this is a set of ordered pairs, and if I was asked to find the inverse of that relation, I would just list the ordered pairs where I'm switching these coordinates. So now 5 becomes my x value for my first ordered pair, and -8 becomes my y value. And then same thing with the rest of them. The second point was 4, -2, so now that would be -2, 4. And the next original point was -7, 1, so that will become 1, -7. Oops. And so forth. So I'm just switching the x and the y coordinates. Okay. Okay, so this next example gives us another set of ordered pairs of this relation G. So in that relation, I have 2, 4, -1, 3, and -2, 0. So in this example, I'm going to graph these points in blue first. So on this graph, I would have 2, 4 would be right here. -1, 3 would be right here. And -2, 0 would be right there. So those are just those 3 ordered pairs in blue. And then I'm going to find the inverse of that relation. So I'm going to write that down here. Which, again, I'm just taking those ordered pairs and I'm switching the x and the y coordinates. So the first point would become 4, 2, because I'm just switching these. The next ordered pair would become 3, -1. And the last ordered pair would become 0, -2. So just switching them. And now if I graph these ordered pairs in red, I get 4, 2 would be right there. 3, comma, -1 would be here. And 0, comma, -2 would be here. So if you look at this graph, it kind of looks like these two sets of ordered pairs. They're like kind of mirror images of each other. And that's true. That'll always be the case for two inverse relations. It'll be like a reflection over this diagonal line that goes through the origin, which is given by the equation y equals x. And that's, it says that on the next page of the notes. So you can write that down now if you want, but it'll say it on the next page. I'm just showing you here that that's true. If I flipped those blue points over that dotted line, they would coincide on top of the red points. So it's a reflection over that line, y equals x. And again, that's always true for inverse relations. And that kind of makes sense because I'm just switching my x and my y coordinates. And the equation of that line is just y equals x. So if I switch them, it'll just flip-flop each other. Okay? So nothing too crazy when they give you a set of points. You're just switching the x and the y coordinates to find the inverse. Okay, but what if they give you a formula or an equation with two variables? So again, we're just focusing on relations right now. I haven't really talked about functions yet. But a relation can be given by an equation as well. So if a relation is defined by an equation, we just interchange the variables. So what does that mean? That means in this example, I have a y and two x's in that equation. So I'm just going to replace the y with x, and I'm going to replace the x's with y's. So really the same thing I did with the ordered pairs, except for now I'm just interchanging the variables here. Okay? And this will produce an inverse relation. Also, I can find ordered pairs on this with this equation here, right? I can plug in values for x, get values of y, and those will give me ordered pairs. Well, in the inverse relation, all the ordered pairs will be switched. All the x's and y's will be switched from the original, which we're going to see after we do this example. So let's do the first step. We're going to find an equation for the inverse of this relation. So I'm just going to replace that first y with an x, bring the equal sign down. I'm going to replace that x with a y, so that'd be y squared. Bring my minus sign down, bring that 5 down, and I'm going to replace that x with a y. And that's it for relations. That would be a formula for the inverse relation of the original equation. Now, when we start dealing with functions, we will have to like solve this for y after we do this. But if it's just a relation, then this would be fine. This would be an acceptable answer. Okay? And again, we're going to see that. Now this picture over here is using what we just did in that previous example. So this first table is the original equation we had, the y equals x squared minus 5x. And then this is the inverse, where we just switch the x's and the y's. So there is a few ordered pairs on here. For example, if I plug in 5 for x into this equation, 5 squared is 25, and then minus 5 times 5 is 25 again, so that's 25 minus 25, that gives me 0. So that is a point on this graph, 5, 0, which is right here on the blue graph. So if that point is on that graph, then the point 0, 5 will be on the inverse of that graph. And that is true because if I plug in 0 for x into my original, then my y would have to be 5. And you can think about it as plugging 5 in for y, because 5 squared minus 5 times y would also be 25 minus 25, which is 0. So x would be 0. And that point is right here. On the inverse graph, which is in red. Okay. And then if I have 0, if I plug 0 over here in for x, 0 minus 0 is 0. So that gives me the point 0, 0. And because both of those are the same for the x and the y coordinate, that point will also be on my inverse. Because if I switch 0 and 0, I still get 0, 0. So those 2 points both lie on each other right there. So those 2 graphs would intersect right there. And then so forth. You can see the other 2 examples. They're just switching the x's and the y's. Okay. And in this picture, they have that dotted line here, which is that line I was telling you about, y equals x. And so in this box up here is where it says that the graphs of a relation and its inverse are always reflections of each other across the line y equals x. So you can clearly see that with the 2 yellow points. If I took that first yellow point and reflected over that line, it would lie on top of the yellow point on the blue graph. And, you know, this is really, you just want to think of it as each point is reflected over that line. And then the other thing it says up there is that we can, if a relation is given by an equation, then the solutions of the inverse can be found from those of the original equation by interchanging the first and second coordinates of each ordered pair. So that's kind of just repeating what I said, which is if I know the points on the first, from the first equation formula, I can just switch the coordinates, the x and y, and find my ordered pairs of the inverse relation. Any questions so far? Okay. So again, this was really just about relations. And why am I stressing that? Well, if you look at this example, the equation in blue, or the graph that's given from that equation, that's a parabola, right? The blue one, which is a function because it passes that horizontal line test. But its inverse is a sideways parabola, which is in red. Excuse me. And that relation is not a function because it would fail the vertical. Did I say horizontal? I meant vertical, sorry. The vertical line test. That one would fail the vertical line test because it would cross through that twice, right? So this is a case where the first function has an inverse that's not a function. Okay, which is fine, it's possible. But when we talk about inverses that are functions, then we need to know a property about the original relation, which is that they will be one-to-one functions. So I need to introduce to you what a one-to-one function is first before we can really talk about inverse functions, okay? Because this is not an inverse function. Like I just said, it's not a function. The inverse is not a function. And most of your homework will be talking about inverse functions. They'll give you a couple of those problems with the ordered pairs and ask you to switch the coordinates, but most of the other problems will be dealing with inverse functions. Okay, so I just kind of reminded you of the test, the vertical line test for functions, right? Both of these pictures of this graph, if I put a vertical line, it'll pass my vertical line test, and both of these graphs are functions, right? Because it only passes through them once. Well, in order for a function to be a one-to-one function, it would also have to pass a horizontal line test. And let me remind you first, let me back up. The vertical line test means that no x values are repeating, right? This is a function, this parabola, but my y values are repeating. So these 2 points have the same y value, which is fine with functions. But for one-to-one functions, neither one can repeat. So the x's can't repeat now, and the y values cannot repeat. So because this first graph here, the parabola, I have y values repeating here, this function here is not one-to-one. And what I just used is technically a horizontal line test, which you'll see down here. So the horizontal line test is used on functions. We already know that they're a function, to test whether it's one-to-one, to see if it will cross my horizontal line more than once. And if it does, then it's not one-to-one. So again, in basic terms, the x values can't repeat and the y values cannot repeat for it to be one-to-one. Now in this definition up here in mathematical language, it says that a function is f is one-to-one if different inputs have different outputs, which is really the same thing I just said. So if these two x values do not equal, if a does not equal to b, then their outputs will also not equal. Everything is unique. And saying that the same way but different, if the two outputs f of a is equal to f of b, well then a has to equal b. It has to be the same. So it just means they have to be unique. Every point is unique. No x or y values can repeat. So in this other graph over here, which is the cubic function, if you remember from our library of functions, this one does pass my horizontal line test. It'll only intersect the graph at one point. So this one is one-to-one. And that might be kind of hard to tell right around the origin, but it's constantly increasing right here. It's not repeating at these 2 points. We just can't really see it that well. But if you zoomed in and kept zooming in on a calculator, those points would be constantly changing. They're like constantly increasing. Okay. All right. Okay, so we're going to learn about some properties of these one-to-one functions. This first box on this last page here is really just about the notation of an inverse function. So if the inverse of a function f is also a function, then we name it this, which we would read as f inverse. So this is the notation you would see in Pearson if they wanted you to find the inverse function. That looks kind of like a negative 1 exponent, but it's not an exponent. Again, this is just notation. It's like giving the function a name, and the name is that it's the inverse of the original. Just like f of x used to be notation. Well, it still is notation, but just like we learned that that's notation for the name of a function in terms of x, that I'm going to say f inverse is notation for the inverse of the original function f. So it is not an exponent. And we will also see it written like this, f inverse of x, which again, this is also just notation. This is just saying that this is the inverse function of the original function f. Okay? All right, so there are some pretty important properties of one-to-one functions, the functions where the x and the y values do not repeat. And that is that if the first one is if a function is one-to-one, so if we know that a function is one-to-one, like that cubic function we just looked at, then its inverse will automatically be a function. So if I found the inverse of that cubic, it will also be a function. And I just know that automatically if the original function is one-to-one. So that's why it's kind of useful to know if a function is one-to-one. The second one is, I just explained that you can use the horizontal line test to determine whether a function is one-to-one. This second property here is another little trick or tip you can use to determine whether a function is one-to-one. And that is if a function is increasing over its domain, so if it's only increasing over its domain, or if it's only decreasing over its domain, then it's automatically one-to-one. So comparing that back to this example, remember we said, well, I kind of said it. This example, if I follow it with my pencil from left to right, it's constantly going up. It's constantly increasing from left to right. Do we agree? This function would be increasing over from negative infinity to infinity. So that automatically tells me this is a one-to-one function. It's never decreasing. But this one, the parabola, it's decreasing on the left because it's going down by moving from left to right, and then it's increasing on the right. So that one is not one-to-one because it's not constantly increasing over its domain or decreasing. It's doing both. So that's another way you can tell just by looking at a function whether it's one-to-one. The next two I would hope is kind of intuitive based on what we did with the ordered pairs. So remember, if I was given ordered pairs to find the inverse, I just switched the x's and the y's, right? So all of my x's, which are my domain, will now become my y values, which is my range, right? So from the original relation, the domain will actually become my range in the inverse because I'm making all those x's my new y's. So that's what this says. The domain of a one-to-one function, the original, becomes the range of the inverse function. And that's what this map says here. The domain of f, which is the original, goes to the range of the inverse. And then similarly, the next one says that the range of the original function, just all the y values, will now become the domain of the inverse, which is all my x values. So that's what that mapping is saying. So that becomes kind of useful if they ask you to find the formula for the inverse of a function on Pearson, and then they ask you to find the domain and the range. If you already knew the domain and the range of the original, then you just flip them. So the domain will become the range, and the range will become the domain. Okay. All right. So now that we've learned all of that, we can now talk about finding the inverse functions of these one-to-one functions. So, I'll just read this. Suppose that a function is described by a formula. If it has an inverse that is a function, then we will proceed as follows to find the formula for its inverse. Okay. So really the first step of this, and you'll see this on Pearson with all these questions, is it'll first ask you, is this function one-to-one? So that's kind of like the first step, really. You need to determine whether the function is one-to-one. And it'll even, like I said, it'll ask you in Pearson, is the function one-to-one? Or determine if the function's one-to-one. So you could either graph it in your graphing calculator and use the horizontal line test, or look to see whether it's always increasing or always decreasing. Okay? Now, I mean, you could also look at this equation and kind of think about it as well. Like, what I'm trying to say is, so none of the x or the y values can repeat, right? So if I plug in two different values for x into this function, do you think it'll ever give me the same output? No. No, because if I plug in any number there for x, it's just going to give me a fraction output. There's no two x values I can plug in there that will give me the same y value, the same output. But like for, just use like quadratic as an example, this one I can plug in two different x values and get the same output, because negative values of x will give me the same as the positive. Like -3 squared is a positive 9, and 3 squared is a positive 9. So that will give me the same output. So you could just kind of think about it, but it does become hard to think about, I will say. So the best way I would tell you to do that is by graphing it. Okay, so we're going to determine whether this function here is one-to-one. So this is a rational function. So let's just kind of review a little bit. What's my vertical asymptote of this function? 5. And more specifically, x equals 5. And so let's say that was right here. So that's the imaginary vertical line that graph will never cross. The horizontal asymptote is y equals 0 because the degree on top is smaller than the degree on the bottom. And so that would be right here on the x-axis. And then if I plug in 0 to that function, this will give me 2 over 0 minus 5, which is just negative 5, right? So that's the point 0, negative 2/5, which would be about right here. That's my y-intercept. And now again, you can just plug this in your calculator and look at the graph. I'm just reviewing how to do this by hand, especially if you need to retake your test. But if I wanted to find the x-intercepts, remember to find the x-intercepts of a rational function, you set the numerator equal to 0, but there is no x's or variables in the numerator. So actually that means that there's no x-intercepts. Because there's no solution to 2 equals 0. There's no solution to that. It's just never true. Okay, so based off of this knowledge, I know that this is just going to go down and never cross the vertical asymptote, and there's no x-intercept, so it must just be going up towards my horizontal asymptote and never crossing it. And then these graphs tend to mirror each other, not always, but most of the time. But I would have figured that out by plugging some more values in, but I'm just going to skip that part. So this is my graph. This is what this graph looks like. Very general shape, or trying to make that look better. Okay. Okay, so in terms of my horizontal line test, do you think that this function is 1-to-1? Yes, it is. It will never cross more than once. So this is 1-to-1, and I'm also going to tell you the other way. So if I'm looking at this graph from left to right, it is constantly going down. It's decreasing, because that left part will be going up, closer to y equals 0. But if I'm looking at it from left to right, it's constantly going down, it's decreasing. And on the right side here, it's also decreasing, it's going down. So I'm tracing it from left to right. So it's decreasing over its entire domain. So the little gap in the vertical line, that part doesn't matter. It doesn't matter that there's a gap. So it kind of like stops doing whatever right there. It just matters that it's decreasing over its entire domain, and 5 is not part of its domain. So it is constantly decreasing over its domain. So that's another way you can kind of tell that it's 1-to-1. And as just another reminder, to determine whether something's increasing or decreasing, you're always looking at it from left to right. Okay? Okay, so this is 1-to-1. Great. So because it's 1-to-1, I know that, well, it has an inverse, first of all, and the inverse is a function, because that's what one of the properties told me. If it's 1-to-1, it has an inverse that is a function. So now we're going to find the this inverse function. Let me kind of move this over a little bit. So we're going to follow these steps up here. So step 1, tells me to replace f of x with y, because we remember that's just what f of x is equal to. It's equal to y. So for step 1, I'm going to rewrite this f of x with a y. Step 2 is to interchange the x and the y. So instead of that y, I'm going to write x. And instead of the x, I'm going to write y. So again, technically this is the formula for the inverse. But when they want me to find a formula for the inverse function, I need to now solve for y. I need to get y by itself so that I can write it in its function notation. So it's just kind of adding an extra step. So now I'm going to do step 3. I'm going to rewrite this here. And I'm going to solve this for y. So I'm going to take steps to get y by itself. Now remember when we learned how to solve rational equations? The first thing we wanted to do is get rid of our fraction, right? We don't like fractions. And the y is in the denominator, so I definitely need to get it out of there. Do we remember how we cleared fractions? Mm-hmm. Yes, kind of. You're on the right track. Yep, you want to multiply both sides by the denominator. But you only need to like multiply it like that on the right side. And then like this on the left side. Because what does that do? So again, right, what I'm doing here is I'm multiplying both sides by the least common denominator. Well, there's only one denominator, that's y minus 5. And why do I do that? Because these will just cancel. Y minus 5 divided by y minus 5 is 1. So that will cancel on the right. Gets rid of it. So on the right side, that's just going to leave me with 2. On the left side, I am multiplying that x by all of y minus 5, so I need to distribute that x to both of those. So that will become y times x minus 5 times x. So at least now I've gotten rid of my fractions. I still want to get y by itself, so what do I need to do now? I could add 5x. To cancel that negative 5x on the left. And that would just give me 2 plus 5x on the right. And then finally, I could just divide by x. Cancel it on the left. And so that will leave me with y equals 2 plus 5x over x. So I've gotten y by itself. So the last step up here is to replace the y with the notation, the inverse notation. So I'm just going to rewrite this y for step 4 as f inverse of x equals 2 plus 5x over x. So this is the inverse formula for the inverse function of the original. Okay. All right, good. Okay, number 2 is f of x equals the cubed root of x minus 2. So let me see here. No. Okay. We can graph this. On our graphing calculator. So I have to do it twice for my video. Okay, so we're going to go to y equals. And in your graphing calculator, if you need to get to a cube root, you go to the math button. And then you go down to number 4 where you see the 3 and then the root symbol. And then we can hit enter. And it will give me that little cube root symbol. And then I'm going to type in x minus 2. And hit graph. And so this is what that function looks like. So if you remember, one of our basic functions we learned in our library of functions was x cubed. And that kind of had this shape, except for it was more vertical. Well, the cube root kind of flips that on its side. So this is what it looks like. And if I were to draw a horizontal line through this graph, it'll only ever cross it once, right? We agree? It's also constantly increasing from left to right. If I just trace this from left to right, it's constantly going up. So it's also constantly increasing. So this function is 1-to-1. Okay. Let me go back. I'm just going to sketch that graph right here for us. So it looks something like that. So this is 1-to-1. Okay, so now we're going to follow these steps to find the formula for its inverse. So the first step, again, is just to replace f of x with y. step 2 is to replace the y's with x and replace the x's with y's. So just interchange the variables. And then in step 3, I'm just rewriting it here. We will take steps to solve for y. So I need to get y by itself. So right now, y is underneath that cubed root, which means I need to get rid of that cubed root. Do we remember how to do that?
Multiply both sides, or cube both sides.
Cube both sides, perfect. Raise both sides to the power of 3, because that is how we can cancel that cube root, because they're inverses of each other, inverse operations. And cubing a cube root will just cancel the cube root and the cube. So on the right, that will just leave me with y minus 2, because those will cancel. And on the left, that will leave me with x cubed. And so the last step here would just be to add 2 to both sides to finish getting y by itself. So this will give, I'm just going to write y on the left side. So this y would be by itself, and then the other side would be x cubed plus 2. And then the last step, step 4, is just to replace that y with the inverse notation, which would be f inverse of x equals to x cubed plus 2. And so that would be the formula there. Well, not without the 4, I guess. And these are my steps I'm following. And so I'm going to show you what this graph looks like on the calculator as well. So let me switch over real quick and then I'll switch back. So I'm going to graph it with this function. So this was the original function. So now the other function was x cubed plus 2, right? So that was the inverse function we just found. So I'm going to hit graph. And so there is the inverse function in red. So again, you can see in the graph that these are reflections of each other through that diagonal line y equals x. And let me just show you even further. I will go down to y3 and I'll just put x, because that would be for the equation y equals x. And I will hit graph. And so there's that line I'm talking about, y equals x. So those two functions are reflections of each other over that line, which is always true for inverses. Does that make sense? Any questions so far? Okay.
When we're graphing these on Pearson, we're supposed to
Well, you don't have to graph the diagonal dotted line.
Okay, so just graph the other two, and it's okay if they're the same color and everything.
Yeah. Well, usually if they are asking you to, have they asked you to graph both at the same time? Usually if they asking you to graph both at the same time, they give you multiple choice.
Okay.
Graphs.
Yeah, I think they did that actually.
Yeah.
I was struggling to graph one of them, and I thought it might be because I.
But they shouldn't be asking you to graph that y equals x line. But again, on some of the ones that give you multiple choice, it'll be there. That dotted line will already be there, just to kind of, so you can kind of see which ones are actually inverses of each other.
Okay. Thank you.
You're welcome. All right, the last one is a little bit tricky. Okay, so the number 3 is given by the equation f of x equals x squared minus 3. And then they have a comma, and they have x is greater than or equal to 0 after it. So what does this mean? So when they give you like an inequality like this for x next to a function, this is restricting your domain. So it's cutting off the x values that they want me to graph this function for. Remember when we did like piecewise functions and we would only graph certain pieces for certain x values? This is kind of cutting off a piece of this graph and only wanting us to graph this function for x is greater than or equal to 0. And why would they do that? Because the original function by itself, f of x equal to x squared minus 3. This is a quadratic, right? Parabola. If I wanted to graph this, I could use the original parabola that goes through 0, 0, and it'd be shifted down 3 units. Remember that? So it'll look like this. And so this function is not 1-to-1. This is not 1-to-1. If it was just like the original x squared minus 3 graph, because it fails the horizontal line test. It would cross that horizontal line more than once. But if they restrict my domain, then I'm only graphing that graph from x is equal to 0, which would be here, and to the right. Because I only want to graph everything that is greater than or equal to 0 for x. So that's what that graph right there looks like. X-axis, no y-axis. We agree? So if they restrict my domain, now this graph is 1-to-1. Because I can draw a horizontal line through that graph anywhere and it'll only cross it once now. So sometimes they'll do that, and usually if they restrict the domain, then it'll be 1-to-1. That's why they're doing that. All right, so because they restricted that domain, and this is one-to-one, I can proceed and I can find the formula for the inverse function. So I'm going to zoom in a little bit. So step 1 is to replace that f of x with y. So this would be y equals x squared minus 3. I'm going to also write down that inequality because I don't want to it's part of this function. It is restricting this function's domain. And I don't want to, yes?
Is there a possible way to like put that into the calculator or no? Into like the graph part of the calculator?
That's a great question, and I really don't know, to be honest.
Okay, I'll Google it.
Yeah, I really don't know. I would say I don't think so, but there should be. I don't know. I've never done it before. Okay. But anyway, so I want to write this here so that I don't forget what I need to do on the next step, which I'm going to explain. So you want to include that x is greater than or equal to 0, because it's part of this function. It's restricting the domain. Step 2 is to replace the x's and the y's, right? So the y will become an x, and the x will become a y. So this will be y squared minus 3. But here, because I had that this x in step 1 was supposed to be greater than or equal to 0, well, now I need to make this y greater than or equal to 0. If I switch the x and the y, well, then I need to switch that restriction now for y. Everybody hear me say that? Okay. So if I interchange those variables, the x and the y, I also need to interchange the variables in the restriction for the domain. So now I will have a restriction on y that has to be greater than or equal to 0. So this will be important when I solve this. But let's continue. So now step 3. I'm just going to rewrite this. And I'm going to solve this for y. So I would add 3 to both sides. And that would give me x plus 3 is equal to y squared. And then I'm just going to rewrite this one again. And then I would take the square root of both sides, right? To get y completely by itself. Well, usually if I take the square root of both sides, I have to have a plus or minus answer. But because we restricted y to be greater than or equal to 0, I only want the positive square root. So I don't want the negative one. So this would just be y is equal to the square root of x plus 3. For y is greater than or equal to 0. And then the last step is to replace that y with the inverse notation, and I'm going to just write it on the left side just because I like it on the left side. So that would be f inverse of x is equal to the square root of x plus 3. And so that would be the formula for, and really you don't need this part here anymore because that will always be positive because it's a square root. Okay, and then also let me do one more thing. Pick a color here. Just just use red. My final answer. So that graph there will actually, this is the square root function. Remember, square root of x usually starts at the origin. And then that plus 3 is shifting it to the left. So over here, actually, let me draw that right here. We draw the graph that we started with, which looked like this. And this graph that we just found, or this function that we just found, which is the inverse function, would look like this. And that is the end of 5.